Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is section 6.4 and it's about present values of annuities. Let us talk about this application first. If at retirement you wanted to receive $1,000 at the end of each month for 16 years, what lump sum would you need to invest in an annuity that paid 99% compounded monthly? We will answer this question in example 1. Well, this lump sum that we need is called the present value of the annuity. Note that the annuity in this case is an account from which a person receives equal periodic payments. In section 6.3, we have seen that the annuity in which we put equal periodic payments and at the end we receive a lump sum. Here we put a lump sum and we receive at the end uh, some equal periodic payments. So in this section we will find the present value of annuities, compute payments from annuities, and find how long annuities will last. These three cases, we will take examples about them. So we have discussed how contributing to an annuity program will result in a sum of money. This is in section 6.3. And we have called that sum the future value of the annuity. Why we call it the future value? Because the lump sum will be in the future. Now, the annuity is used also to describe an account from which a person receives equal periodic payments, withdrawals. So we say annuity when a person puts equal periodic payments and get lump sum at the end in the future, or when a person puts lump sum now in the present and get or receive equal periodic payments in the future. So if you invest a lump sum of money in an account today, so that at regular intervals you will receive you will receive a fixed sum of money, you have also established an annuity. And this sum of money that you require to purchase an annuity is called the present value of the annuity. And we will talk here in this video about present value of ordinary annuities. So suppose we want to invest a lump sum of money, and let us denote it by AN, in an annuity that earns interest at rate I per period, so that we receive payments of size R from this account at the end of each N periods. And notice that when we receive at the end of each N periods, we call it ordinary annuity. And after we receive, after the N periods finishes, of course, there will be nothing in the account. The balance of the account will be zero because we received all the money in the account as equal payments. Okay. Receiving payments at the end of each period means we are dealing with an ordinary annuity. So what is the present value of an ordinary annuity? This would be the formula. AN, the present value, equals R, which is the payment, okay, the payments, the deposits, not the deposits, not the deposits in this case, because we do not deposit them, we receive them, so we call them the payments. R made at the end of each period. N is the number of periods, and I is the interest rate per period, as in section 6.3. So the account is an ordinary annuity, and this will give the present value. If you remember, the formula for the future value is R, the deposits, times 1 plus I to the power n minus 1 over I. So what happened here? R is the same, but here it is payments, not deposits. I is the same. Instead of 1 plus I to the power n minus 1, we have 1 minus 1 plus I to the power negative n. So you can say that this minus 1 becomes positive, and this one becomes negative, and n becomes negative n. Okay, so we 1 minus, instead of 1 plus I to the power n minus 1, it is 1 minus 1 plus I to the power negative n. So this is the formula for the present value of an ordinary annuity, and we can use it now to find AN given this information, or to find R if AN is given, or to find N if AN and R are given. Example 1, find the lump sum that one must invest in an annuity to receive $1,000 at the end of each month for the next 16 years. So this is R, okay, and this is 16 years, this is the time. If the money pays 9% compounded monthly. Monthly means 12 times per year. So N would be 12 times 16, and 12 times 16 is 192, and I would be 9%, 0.09 over compounded periods, which is 12, okay, or number of compoundedness, which is 12. So 0.09 over 12 is 0.0075. So we need to find the present, find the lump sum. That's the present value of the annuity. Okay, the payments are given here, 1,000. So AN is equal to R, which is 1,000 times. We start with 1 here, minus 1 plus I. Well, it is 1.0075. This is I, and 1 plus this would be 1.0075 to the power negative n, and n is 192 over I, which is 0.0075, and you put this in the calculator and you multiply, and the result would be 101,572.77 So 101. So it is important to note that all annuities, we have two kinds of annuities now, okay, in section 6.3 and section 6.4. All annuities involve both periodic payments and lump sum, okay, of money. But if the lump sum is in the present, then we call it the present value of an annuity. And if the lump sum is in the future, we call it the future. We call the lump sum the future value of the annuity. So this sum is called either the present value or the future value, the lump sum itself. Another example, suppose that a couple plans to set up an ordinary annuity with 100,000 inheritance they received. So this is the lump sum, okay? And they have it now, they received already, okay? So this is the present value of an annuity. What is the size of the quarterly payments? So we need R. The size of the payments is R. Quarterly means 4 times per year. They will receive for the next 6 years. So N is 4 times 6, that's 24 periods, while their children are in college, okay? If the account pays 7%, so I is 0.07 over 4. And if you put this in the calculator, it is 0.00175. So we have AN in this case, and we need to find R. R is multiplied by 1 minus 1 plus I, so it's 1.0175 to the power n, negative n, which is negative 24, over I, which is 0.0175. And then R would be 100,000 over this amount. Okay, you can calculate this amount first and then divide 100,000 by it, and then you will get the answer. R would be 5138.57 dollars. These are the equal payments they have to put, they will receive, after 6 years. Not after 6 years, they will receive for the next 6 years. Okay, they will put 100,000 now, and they will receive for the next 600 years this amount, this payment each quarter. Suppose an annuity pays, so the annuity pays $2,000. So this is R. Okay, at the end, so this is ordinary annuity of each 3-month period. 3 month, how many 3 months in the year? 4. So quarterly, so 4 times per year, 3.5 years. So what is the total number of periods? N would be 3.5 times 4, and 3.5 times 4 is 14. Worth 4% compounded quarterly. So what is the interest rate per period? I would be 0.04 over 4, so it would be 0.01. What formula is used to find the present value? This is the formula of the present value. Find the present value. R is 2000. You just put the information. 1 plus 0.01, so it would be 1.01 to the power negative 14 over 0.01. And if you put this in the calculator, you get the answer. Okay, the answer is 2,6,007.41 dollars. Another question, an inheritance of 400,000. So this amount is present, is now, they have it now, will provide how much at the end of each year? So this is ordinary annuity for the next 20 years. So they will put this amount in the bank, and they will receive in the next 20 years at the end of each year how many? Okay, if money is worth 7%. So what is N here? compounded annually. So n is 20 years times 1, 20, and I is zero point zero 0.07 over 1 because it's compounded yearly, annually. So I is zero point zero 0.07. And he is asking about what? How much at the end? So he's asking about R. So this is AN is given. So 400,000 equals R times 1 minus 1 plus I, which is 1.07 to the power negative n, so negative 20 over I, which is 0.07. And you find R by dividing 400,000 over this amount using the calculator, and you will find that the answer is 37757.17. So $37,757 per year they will receive at the end of each year for the next 20 years. An inheritance of 250,000, so this is the present value of an annuity, is invested at 9% compounded monthly. So I would be 0.09 over 12, and 0.09 over 12 is 0.0075. So this is the interest rate per period. And if 2,500 is withdrawn, so this is R, at the end of each month, so this is an ordinary annuity, how long will it be until, how long? So he's asking about N, how many periods will it be until the account balance is zero? The account balance is zero means you receive all the amounts. Okay, so 250,000, this is the present value. R is 2,500 times 1 minus 1 plus I is 1.0075 to the power negative n. The number of periods now is unknown over I, which is 0.0075. So how to solve this equation now for n? Well, I can first divide the two sides by 2,500. So if you divide 250,000 by 2,500, you get 100. And then I can multiply now cross product. Okay, I multiply by 0.0075, or you multiply both sides by 0.0075 if you like. So 100 times 0.0075 is 3 over 4, or 0.75. Okay, now I'll take this to this side and bring this here. So I will have 1.0075 to the power negative n equals 1 minus 0.75, which is 0.25. And now I apply ln to both sides. And why we apply ln? To be able to take negative n outside using the properties of ln. This is 0.25, just 0.25. So negative n would be ln 0.25 over ln 1.0075. And this would be negative 185.53 using the calculator. So N would be 185.53 what monthly months. So how long will it be until the account balance is zero? It will be, or after, you can say after 186 months, account would be zero. Okay. After 185, it will not be zero because there will remain some small amount. But after 186 months, the account, there would be nothing in the account, nothing left in the account. Find the present value. So he's asking about AN of an annuity of 6,000 paid at the end of each 6 month at the end. So this is ordinary annuity, 6 month period, so twice a year for 8 years. So N is 2 times 8, that's 16. If the interest rate is 8%, so I is 0.08 divided by 2 because compounded semi-annually. So I is zero point zero 0.04. So what is AN? You just use the formula. R is 6,000 times 1 minus 1 plus I, which is 1.04 to the power negative n over zero point zero 0.04, and you put this in the calculator, and the answer would be 69913.77. How much is needed in an account that earns 8.4% compounded monthly? So I would be 0.084 over 12, and this would be 0.007. To withdraw, so this is R. So how much is needed in an account now? Okay, so this is AN. He is asking about AN, the lump sum. Withdraw 1,000 at the end of each month for the next 20 years. Okay, so N here is 20 years times 12, the number of months, and this is 240. So there are 240 periods. So AN would be 1,000 times 1 minus 1 plus I, so 0.007 to the power negative n, so negative 240 over 0.007, which is I, and the answer would be 116 and $76, 116,000. With a present value, so this is AN, what is the size, so what is R, of the withdrawals that can be made at the end of, so this is ordinary annuity, each quarter 4 times per year for the next 10 years. So N is 4 times 10, 40. If money is worth, so I is 0.064 quarterly, compounded quarterly. So I divide by 4, and when I divide by 4, I get 0.016. So I have the present value given, and R here is unknown, times 1 minus 1 plus I, which is 0.016 to the power negative 40, because N is 40, over I, which is 0.016. And as we did before, R would be the division of 135,000 times this amount, and the answer would be 4,595.46 $4,595. A professional athlete invested 2.5 million of a bonds in an account. So he has this amount and he invested in an account that earns 6.8% compounded semi-annually. So I is 0.068 over 2. This is the interest rate per period, and it would be equal to 0.034. If 120,000 is to be withdrawn, so these are R, okay, the payments, what he will get withdrawals at the end of each 6 months, so twice a year, okay, each 6 months, twice a year. So n would be, how long will it be? Okay, so n is unknown. So an is 2.5 million. I will multiply 2.5 times million, so I have 2,500,000 equals R, which is 120,000 times 1 minus 1 plus I, which is 1.034 to the power negative n, which is unknown, over 0.034, uh, which is I. And now we need to solve for n. So as we did, we will divide 2,500,000 over 120,000. And then we multiply by 0.034. And the answer would be 17 over 24. So we will have 17 over 24 equals 1 minus 1.034 to the power negative n. And then 1.034 to the power negative n will be equal to 1 minus 17 over 24, and that's 7 over 24. And we apply uh, len to both sides. So negative n would be len 7 over 24 over len 1.034. And if you put this in the calculator, you will find that the answer is negative 36.85, and this means that n is 36.85 uh, half years. Okay, so how long will it be? 30. It would be until the account is zero. Account will be zero after 37 half years. You can say, if you want, 18.5 years if you divide 37 by 2. How long will an account worth? So he's asking again about n worth 2.2 million. Okay, how long will an account worth? So this account worth 2.2 million. It has 2.2 million now in the present. So this is an. Provide. So how long will this account provide 10,000? So this is R at withdrawals at the end of each month, ordinary annuity, if money is worth 5.4 compounded monthly. So I is 0.054 over 12 because it's compounded monthly, and this will be 0.0045. So we have AN 2.2 million, so that's 2,200,000. R is 10,000 times 1 minus 1 plus I, so 1.0045 to the power negative n over I, which is 0.0045. And as we did in the previous question, please try to solve it by yourself. We will get that after we solve, we will get that n is 1,255.67 what month. Okay, so if how long it will take, it would be 1,260 months. Okay, that's the end. You can change it to years, you can leave it in months as you wish. Uh, that's the end of this part, which is the present value of uh, ordinary annuity.